Hi folks, and welcome to episode 2 of AutoFocus. It looked like episode 1 went down well, so we're going to carry on. So yeah, just brief recap. Episode 1 was stripping car down to its body shell with no parts on, then media blasting that body shell, stripping all the underseal off, media blasting it, getting it back to bare metal, then putting a bit of etch primer on it. We explain why we did those processes. We're going to come back to some questions at the end of this episode actually and touch on some of the questions that were asked. That leads on to the next stage of the process. We're going to try and do a lot of this series in chronological order, but not all of it. Some of it's going to be out of sync. I was trying to weigh up whether to do an episode on an actual process or whether look at some of the equipment needed to do that process, but we've decided to do the equipment as we go. So one of the next steps on that process, on that restoration process, will be the metal work involved on the body shell, body tub, whatever type of car it is. It's normally a body shell, and a lot of them are steel. Not all, but many. The bulk of what we deal with are steel body shells, at least semi-monocoque, generally monocoque that we deal with. So the next stage is to do the metal repair. Now, some of the time that'll be fixing in complete repair panels, and we're going to cover that in another episode. But one of the early stages, which is pretty critical for anybody to be able to do in repairing a monocoque body shell, is making repair sections to fit into an existing panel, i.e. not a complete panel, where a piece has to be let in, and that would generally be butt welded in place. And probably, I would say a good percentage, more than 50% of the time, that's a key skill to be able to do. More than 50% of the time that we're repairing panels, we're actually adding sections in, and we're splitting a panel and doing a butt welded section in that panel. And around me here, we've got a few examples that I want to pick up on. I'm going to swing this way. This is a bit dirty, I haven't cleaned it, I haven't had time. It's a bonnet for the Land Cruiser that's just over there. People who watch the Uncut series will have seen this in that series. This had some rust along the front edge. Now Tom made a new section, the whole front piece for this bonnet along here, and you can just about make out a shadow line along there, which is where the butt weld is. Now that was butt welded into the front of that bonnet. Pretty skilled job Tom's done of that, and as you can see, it's barely visible where that was let in. So that's the sort of repair that can be done where it's quite tricky to do any other way. And buying a whole bonnet, we did actually get another bonnet for this, and it was in worse condition than the one we already had. When new panels aren't available, generally part of the work involved will be to repair them by butt welding in a new piece of material. So there's an example of one that's finished, and then here's some work in progress. This is for the Churchill Mark II Jaguar Coupe that we're building. So here's a half rear quarter panel. And because of the curvature, it's possible to do this we're splitting it lengthways, so this is a half quarter. I can't actually remember whether this is the front half of one side of the quarter panel for the car. We're actually doing a lap joint along the top under a trim strip. That's an aside, there's a reason for that. But this along here, as you can see, there's a butt weld line here where this section is butt welded to this. It was easier to make this in two halves rather than having to try and put all of this shape in and risking if there was a problem in getting the shape into the panel, particularly with this return on it, then you risk scrapping the whole panel, whereas if you just weld it together afterwards and then planish the weld out, it's a bit quicker and a bit more of a secure process. There's less risk in causing a problem with the rest of the panel because there's a bit of detail on the front of this panel as well, and we didn't really want to damage it too much. So that's why that was done that way. And then literally, just a little bit earlier, so on film very shortly, is a bit of footage of Tom processing this piece, welding this upper existing Jaguar door section, which has been extended, onto the upper half of a door skin. This is the lower half of the skin here, and that is then going to be grafted onto this. So we'll actually put two weld lines into this panel. It could be done as one. It's very difficult to do as one. It could be done as two, which would be a bit easier. And it can be done as three, which is easier again, although more weld finishing, more planishing involved. And that shouldn't be a problem. As long as the welds are done properly, and that's what we're going to go into, then the planishing isn't really an issue. So that's a panel which we're going to be welding together very soon, and this particular weld line here Jamie's got some footage of, which we'll show you now, of that actually being done. And then once you've seen that footage, I'm going to go into the detail of how you would go about doing that. And you don't need particularly expensive equipment. You need a reasonably bit of expensive equipment. You really need either a Tig Welder or oxyacetylene equipment. But as long as you've got that, and we'll go in a future episode into why you probably should have that if you're building cars, then the rest of it's pretty cheap to do, just hammers, dollies and some metal. So there's a bit of footage now of that actually being done, and then I'm going to demonstrate the exact reasoning why we do that the way we do it. Right, so you've seen Tom welding that panel together, and I will explain the process now as best I can. I'll probably miss something and have to go back on myself as I usually do, but I'll explain the process and the equipment needed to do it. So the basic process of butt welding a steel panel together is that you tack the panel together initially, and whilst tacking it, you accurately set the relationship of one edge of a panel, these two pieces of metal being an example, you accurately set the relationship of one of them to the other one. So you accurately set that during the tacking operation and make it so they can't move during the full weld. Once you've done that, and you use the hammer and dolly to process those tacks as you do that, which I'll explain properly in a minute, and you then do a full weld, the full length of the panel in one go, you then weld it in one go, and then you planish the weld to finish it. So the equipment you need to do this job, it can be done a number of ways, but realistically, to make a really tidy, really nice job of it, you either need a Tig Welder or oxyacetylene equipment. The Tig Welder is what we use. We don't have acetylene on this site. We have obviously propane, but you can't weld with propane. It has to be acetylene. So we actually use Tig for all of our panel butt welding that we do here, apart from the very odd occasion where we have to use MIG for some obscure reason, but we will generally use a Tig Welder. So to my right here is a Tig Welder. This isn't an enormously expensive machine. It's a very old one. I'll say old, 1990-ish. And it's a Hitachi machine. You don't need, none of that's really very relevant. The relevant bits to the job are you need a Tig Welder with normal DC output. It's very helpful if it has high frequency start, in that it means that you don't need to scratch start the tungsten each time you start. And it needs to be controllable at quite low amperages. On this, these are pieces of 18 gauge steel, which is 1.2mm thick steel. On that, I'm going to be probably welding somewhere in the region of, I don't know exactly without watching the gauge, but I would say I'm going to be somewhere in the region of 30 amps, 25 to 30 amps, not very many amps. So it needs to control well at low amps, which that does all of. However, a pretty cheap DC inverter Tig will do that job. You know, you can get one off eBay for sub £500 that will do that job absolutely fine, no problems at all, day in, day out, and not give you any trouble. You know, you've got to be a bit careful what you buy, but there are machines out there that are relatively cheap that will do that job absolutely fine and be no worse at it than a pretty expensive state-of-the-art Tig, which this one sort of kind of is, but it needn't be for this job, because this is a pretty straightforward job. I'll try and go through briefly what I'm using equipment-wise. There's a water-cooled torch on this. Again, it doesn't need to be. I use a gas lens for all this work rather than a... I won't go into all the detail on it about the Tig bit. There's plenty of information, videos on YouTube. The Welding Tips and Tricks channel with Jody on Welding Tips and Tricks. He's brilliant for explaining a lot more detail about TIG welding. If you need to know a bit more background to the process, he goes into that quite a lot. I'm using a gas lens rather than a collet body in there. It just gives better gas flow. I'm using a 2.4mm, 2% lanthanated tungsten. And I can't even remember what size. It's got a number 6 cup. Not that it really matters for this job, it's not that important. I'm using pure argon at around 14 litres a minute. Gas flow. As I say, I'm running with foot pedal to control my amps, and I set it slightly above what I'll ever need. So I've actually got it set for 50 amps max, so that I've got plenty of travel on the pedal. And when I'm tacking, I probably will use a brief period of that full amps to do my tacks. So I set that to 50 amps, but actually when welding continuously, I'll never be using that at 50 amps. As I say, water-cooled torch makes it lighter and easier to manoeuvre. That really doesn't matter though, it doesn't need to be to do the job. My earth's going to the table, so the work is all earthed on the table. So that's all that. I think I've kind of covered everything from the sort of technical equipment side of things. Now come over, obviously, you need a welding helmet of reasonable quality because you need to be able to see what you're doing. A lot of people forget that and try and use a dirty helmet where you can't actually see what you're doing. It doesn't need this to get very dirty before it's extremely difficult to see. And you'll tell yourself you're not doing a very good job of welding when it's actually the fact that the helmet's just dirty. So get a decent welding helmet. It's worth spending a few quid. You don't need one this good. These are 370 quid, I think, now for this particular speed glass one. You can get ones for around the mid to high £200 mark that are very, very good and that will keep your eyesight fine and that do a really nice job and that the consumables aren't too expensive for. You have to be careful with that. If the lenses are too expensive, you'll be tempted not to change them and then you won't be able to see what you're doing and there's no point having the expensive hat. So there's that to bear in mind as well. And then the final bits of equipment are, you need a planishing hammer. This is a really good little one. A very small planishing hammer is perfect. Don't get a great big heavy thing. And you want one with ideally with a flat face one end and a slightly crowned face the other end. The slightly crowned face is very important when you're coming to stretch these welds shortly, which I'll show you as I do them. The slightly crowned face is very important for doing that. And then you need a dolly of some sort. This is just a beaten up old thing, which is got a slightly concave face that side, but it's more or less flat. It'll be fine for putting on the back of a weld just to tap it out. Ignore it's a right state, this thing, but it's fine for tapping some welds up. So it's that. And then in terms of welding material and welding material, this is just plain old 18 gauge, so 1.2mm thick, cold rolled mild steel sheets. Right, silver, it's cold rolled, which basically means hot rolled sheet. It comes off a mill while it's hot, hence the name. and because it's hot, as it comes off, it makes a mill scale on the surface. The oxide forms on the surface, and then that forms a layer which you can't weld. You have to grind that off first. So cold roll steel is then steel that's gone through the hot rolling process. They then pickle it to remove the mill scale, and then they run it through rollers cold to size it down to the required thickness. And because it's run through the rest of the process cold, it doesn't pick up oxide, hence it's nice and clean. Get that stuff, it's miles easier. We buy it in 2 metre by 1 metre sheets from a local steel supplier, Tamworth Steel in Tamworth, and they're great to deal with. And yeah, it's just cold rolled mild steel, nothing too fancy about that. The rod I use, this is it's a SIF rod. It really, again, isn't too critical that it's a SIF rod. This is SIF steel, Tig welding rod, and it's an A18 Tig welding rod, which we use for most of our Tig welding work, mild steel Tig welding work. It's an A18 rod, so it can do structural work right down to just plain old panel work like this. It's a pretty all-purpose, decent quality rod. You don't particularly want to be using, some people, it's possible to do this with MIG wire, but if you use cheap MIG wire, it's liable to have oxide in it. And also some of the real cheap and nasty TIG rods sometimes aren't very good quality, and you end up getting oxide inclusions because of the rod not being very good. So it's better to just buy a reputable rod. It's not particularly expensive, so you might as well get the decent stuff. So that's that. I think we've probably got everything there. So I'll go into a bit of a detail about welding these pieces together. So get your 2 pieces of steel, make sure they're fairly flat, that they line up. Now obviously this is a very simple piece, it's just 2 tiny bits on the bench, so it's dead easy to line up. The theory stands for however big the piece is, you need the edges to be in line. If you run your finger over them, they need to be level and flat. If one's higher or lower than the other, it won't work. You know, you have all sorts of problems. They need to be level, and they need to be prepped completely clean. We have a guillotine, these are cut on a guillotine. If you can't cut with a guillotine, second best is a set of really good, really sharp tin snips. Preferably like the Gilbo type old school tin snips that don't put serrations in the edges. The cleaner the edge, the easier it is to weld well. So good old fashioned Gilbo type unserrated tin snips. Failing that, if it's difficult to cut and you're in corners and difficult places to cut with tin snips, then the aero ones are okay with the serrations. They're just not as good, but they'll do the job nicely. Beyond that, you really don't, ideally, you don't want to be trying to do this on ground edges. Now, we do that sometimes, but you don't really want disc-cutted edges if you can avoid it, because they're never straight. The straighter and simpler you can get the edges, the easier it is to weld. So preferably guillotine, failing guillotine, really nice tin snip cuts. If you've got 2 panels that you just can't do a nice straight cut on, and you've got to cut them together so that they match, so that they're a part that's been cut together in situ, rather than cutting them together, which is what some people do. They would lay the panels over and then air saw through them. That's one way of doing it, but you inevitably, to get the panel alignment accurate, you end up with a small gap where the blade's gone. So what we would tend to do, or what I tend to do, is rather than trying to cut them together, is lay them together, make sure they align, scribe along the edge of one onto the top of the other, take them away, and then if it's impossible to cut and absolutely crack on the scribe line first time, it should be possible with tin snips, but if you can't for some reason, then cut it slightly to the waist side of the line, and then very, very, very carefully sand it exactly to the scribe line. It has to be perfectly accurate. The absolute key to doing this is complete accuracy on the prep of the cut line. It has to be perfect. If it's not, literally throw the bit straight in the bin. There's no point wasting the electricity on the welder to try and weld them. If the cut line isn't perfect, start again, because the job will fail if the cut line isn't perfect. That's absolutely key. So once you've got that, obviously this is dead easy, 2 straight little pieces, butted together. Now, you can set a gap on them by setting a gap initially. What I tend to do, I know Tom tends to set a gap initially, what I tend to do is just put the bits together and tack them straight away, because I can adjust the gap with the tack, as I'll show you in a minute. So what we're going to do is blind Jamie now. You're going to be all right working with this? I'll give you a warning.
It's already archived.
Right, mind your eyes then. So, what we've done there is we've struck up an arc, we've created a little weld pool, and we've just put a tiny dab of filler rod into that. The pieces were just touched together when I did that. There's no hurry to this next part of the process. Those 2 bits are now tack welded together, and that bit there will be pulled incredibly tight together now. Now we can adjust, what we're going to do is put it on the bench because the bench is quite cool, so it'll cool down a little bit quicker. I'll let that cool down a bit. Then I'm going to tap that weld up. What we've done is we've created a little lump of metal there. If we compress that against something, either the table or what I'm going to do is tap it on this dolly. If we put that on there, now it's cooled down a bit, and tap that, obviously that metal is going to squeeze down. When it squeezes down, it's going to spread apart. As it spreads apart, it's going to open up a gap there. So if I hold that right up to the camera, you're going to be able to get focused on that. See, those pieces are absolutely tight together now. So what I'm going to do is I'm going to bring that back down, I'm going to put it on here, and then I'm going to use the crown side of my hammer, and I'm just going to tap that up on there now. Like that. Now, it'd be hard to see on camera, but what it's done is actually created a tiny gap there now. There's a very, very small gap there now. It's barely visible, but there's a tiny gap there now. And what you'll see now is that those two, I'm going to exaggerate it just for the benefit of film, those two pieces have now scissored apart. So the gap opens up as you go down. So what I'm going to do is I'm going to put another tack on that now. So note, keep an eye on the fact that how far apart those two pieces are. Now I'm going to put another tack on now, about 1 inch along from that one, and we'll see what this does. So mind your eyes, Jamie. If you watch these pieces now, as that cools down, watch what happens there. They're tight together again now. So I'm going to let that well cool. I'm going to put it on that dolly again. I'm going to tap that tack up until they open up again. And then I'll explain a bit more. That's because the table's cold, that's cooling down quite nicely. Yeah, you're all right. So using the crown side, so maximum stretch. With the crown side, it'll pinch the smallest possible area because I'm on a radius dolly with a radius hammer. So it's going to pinch the smallest possible area and give the maximum stretch to that weld. So I'll stretch that weld back up. As you see there again, we've got a gap back, look. So now I can go and do the next tap. I'm going to go all the way along doing that. Very slow process. On a large panel, it's an incredibly slow process. I'm going to do another tap about 1 inch further along again. And it'll pull this back in. Now, as you can imagine, if I did that, watch your eyes, Jamie, a minute. If I'd done this without tapping those tacks up as I went, and I just tried to weld the two things together, by the time I got halfway along, they would be overlapping. I'm not going to demonstrate it because it would be very difficult to get back. But if I'd done those 3 tacks and not tapped them up, by now these two pieces would be overlapping each other. And that would be a major problem. What we're trying to do is get the gap exactly right as we go. So I'm going to just let that cool down a bit. I'm going to be fighting time a little bit to keep this not too monotonous. But, so tap that. You really want to let them cool off before you tap them up, because if you tap them up hot, then it's still going to shrink back. It still is now, look. That's still actually coming back a little bit now. So tap it up while it's nice and cold. And we'll do the next one. And I'll try and do a couple more before we move on to welding it. But, so mind your eye. We'll do another one just there. Another tack just there. I'm going to do a really small tack so we can crack along a little bit. And again, watch the gap. I can see that moving in. Gap's closing up as that cools down. And it's pretty much stopped moving at that. And that's, I can touch that now because this bench is cold. So then we'll tap that back up, open up the gap again, drop it back down. I'm going to crack on as fast as I can now. Mind your eyes again. Another tap, like that. Let it cool down a little bit, watch the gap close up. Don't insert any bits of your skin or anything in the gap because it'll cut it. Right, that's cool enough to touch again. And we'll tap it up like that, gap's open back up. And it's basically, however long the panel, however big the job, it's the same theory every time. Just stick the tack on, wait for it to cool down. You'll notice I'm just pausing with it. It doesn't really matter on this demonstration piece, but once you get into the habit, you just do it anyway. I'm pausing over the weld after I've finished it. That's just letting the gas, the after timer gas, go onto the weld, which stops it oxidizing, so they're all nice and clean. That saves me then having to clean a load of oxide off when I come back to do the final weld. If you let these oxidise around them, then you'll have to clean it all up when you come to do the final weld, because you don't want any oxide in the final weld. Another inch along, we'll do this one more and one more, then we can stop that. Those eyes, and we'll put the tack on there. And what you can do is you can play with the gap a bit. And what I actually noticed on the last one is actually the gap started to stay wide, so I'm not going to bother tapping that one up because the gap is actually already wide there. So I'm just going to do the last one, and that cools down a bit. We'll put one more on here, like that. I'll let that cool down. I am just going to tap them to get them level once they've cooled down a bit. And you can see we've got a slightly varying gap. It's just slightly open there, but it's plenty good enough for to do the job. So I'm just going to tap them up very, very lightly to make sure they're level. But at that, we've now got a nice setup. So they're all tacked up, all tapped, and the gap, it does open actually very slightly though. I probably over-tapped that tack. But basically the gap's now pretty even, I have to say. It could have been better there, but so that's now done. If I hadn't tapped any of them up, that piece would probably be overlapping by 5mm there, and you'd be bending it, trying to stop it overlapping, and then it would twist, and that panel would never come out straight and true. So then once that's done, and this is the bit that people get surprised by, is it needs to be welded. And to weld that, we just weld it from one end to the other. So I'm going to try and do this, and I haven't actually done a lot of TIG work for quite some time. We should be able to weld most of this without any filler rod. We should be able to just fuse weld it together. I'm going to keep the filler rod. You never want to try and do it without having filler rod in your hand. It's one of those jobs where the weld will know. If you haven't got a filler rod in your hand, the weld will know and burn the edges back. If you've got a filler rod there, chances are you won't need it. Always keep it in your hand, even if you're planning on fuse welding, just have it there ready. So then we're going to try and weld this together, and I'm going to try and not make a complete mess of it. I'm actually just going to put a weight on that because it's going to start moving. So I'm just going to put them on there to stop things moving around, and then we'll have a go at welding it. So I'll go into probably in the future into a bit more detail on TIG welding, but basically you can see the angle I'm holding the torch at. That's something like the right angle. You want it reasonably vertical. If you point the arc too far forwards while you're going, it tends to form like a half moon weld pool that climbs ahead on the sides of the weld seam and causes you problems there. So you need the torch reasonably vertical while you're doing this. And I'm just moving forward. I just move forward and dab, move forward and dab, move forward and dab, move forward and dab, and keep going. And you really want to try and do this in one hit. I'm struggling to slide my hand a bit on the bench here now. I should have got myself organised a bit better with my slidey rail, but I'll be all right, I think. Yeah, there we go. It's going along nicely. I'm now picking up a bit of reflection on the back of my helmet, which isn't helping. I didn't realise I haven't done any welding at this bench yet, and I hadn't realised how much the light actually reflects on the back of my visor. There we go, we're going along. Now we just keep going. I am using filler rod actually. Having noticed how this seam's going, I am actually using some filler rod. You have to play this bit by ear as you go. You can't really prejudge whether you're going to need it or not until you actually start the weld. You have to see how much is dropping through to the other side, how you've got the welder set. That's one of those things where lots of practice on scrap material is what you need to do to be able to know exactly how that's going to go. And stop there. So that is now slightly rough and readily welded. I've done better jobs, but it's stuck together. So then that's done like that. So your two sides of your panel are now joined together by a weld. And the key bit for knowing whether you're going to be able to planish the panel up nicely afterwards, the key is if that heat affected band is nice and even. Now I've got a dip there, a little bit of a dip there, but it's not too bad. If that heat affected band is nice and parallel, the chances are that you've applied the same heat all the way along, you've put the same amount of filler rod in all the way along, and you should be able to planish that out really quite nicely and make a neat job of the finished panel joint. So you've got to let that cool down a bit. Just turn it over while we're waiting to do that. You can see it's pulled up a little bit. You can see that there's some weld dropout along most of the way along the back, a little bit light there. I probably didn't have quite enough heat there. Which is interesting. You can see where that's gone narrow, where exactly at the point where it's only just dropping through. So you can see though that that's a pretty reasonable weld, and that's how we would do nearly all of our patch repairs on external surfaces of the car. Obviously some of the more structural parts of the car we would do just with a MIG. You know, there are areas where they're just a structural part, it's a very small patch. Sometimes we would butt MIG a section in, but most of the repair work we would tend to do this way. We would tend to TIG weld the repair sections in, just because it just makes a neater job, and the finishing, the weld finishing, is so much quicker. I mean, I'll demonstrate planishing a bit of this. I'm not going to planish all of it now because it makes a lot of noise and it'll just be me hammering on a video for some time. Just check that's cooling off reasonably well now, so I can demonstrate a little bit of it. I'm actually going to do this on this dolly. I would normally do it on a stand dolly. In fact, to tell you what, we're going to quickly wander over to the stand dolly, I think. The aim of the planishing is to, again, a little thing I didn't explain very well actually over there is I was talking about stretching the weld. The reason we need to stretch the weld is when you deposit metal, you're depositing the metal in the weld seam at the melting, say 1400 degrees C, let's say. I mean, it may be more than that, it may be less than that, but let's say 1400 degrees C. Steel has a coefficient of expansion. So if you deposit it at 1400 degrees C, it will shrink by its coefficient of expansion back down to an ambient temperature. It would be really nice if you could deposit the metal at ambient temperature, then it wouldn't shrink, but you can't. So when it shrinks, then it pulls the material to itself, which is why this panel is distorted. So the way we get that back is we use the excess thickness of material that we've deposited, and we use a hammer to thin that material down and stretch it, roll it out like pastry basically, so that it lengthens and gives us the material back. So I'm going to use the crown end of this hammer and just lightly go along there, just lightly stretch this weld seam to stretch that material back. And we'll turn it over and do the same from the back. I'm not going to do all of it because it will bore you witless, but I'll demonstrate the first part of this seam, I'll demonstrate, and then I'll just show you. So as you can see, that's now pretty flat. There's not a lot of excess material there. And then I'll use the flat side just to tidy that up a little bit. Say, I'm not going to do the whole lot, but as you can see, that's coming up nice and flat. I'm literally going to grab my glasses, which I've put down somewhere. Bear with me 2 seconds, stay there, Jamie. I'll be back in one moment. I'm actually going to use Tom's glasses. And I'm just going to buzz over that with a grinder. Now we could, if you were doing a really professional job on a panel on the car that needed to be perfect, you'd probably just file it, but just to demonstrate, the sort of result you get. That's, as you can see, I haven't completely finished it. You could then planish that up again and finish that a little bit better. But as you can see, that is now more or less flat, more or less free of distortion, and a reasonably clean seam. As I say, you don't need to, these skills are not that hard to learn. I mean, I've done it for a while, but the last time I welded a panel like this was at least 8 months ago. So it's, I'm not a miracle worker. It's not that hard to do. It's perfectly doable in your garage, at home, on your own car that you're restoring. It takes a little bit longer than just slapping some MIG repair on it, but it means you get a proper job done. It's really strong. Panel looks nice when it's all done, and you can be pretty proud of it. So that is very, very quick summary of how to butt weld a panel repair. I think that pretty much covers it. Yes, that's a very simple, really simple piece to do. Much harder when it's a nice big curved panel on a car that's really tricky, and I can almost imagine people saying, yeah, but try doing it underneath a car on XYZ. The key is make it easy for yourself. Take the panel off the car, unspot weld it, repair it off the car, re-spot weld it back on. Take the car apart in order to do the repair work, make your life easy, and then you'll be able to do a nice job of it. It's always the case with welding, is the easier you can make the actual weld, the nicer the job nicer the result you'll get. So focus on trying to make your life easy while you do it. I hope that's enlightened people a little bit. Any questions, and I'm sure there'll be thousands because it's such a broad subject, and rest assured we're going to cover quite a lot more on this. Probably not more in detail of that's how we butt weld a panel together, but we're going to cover quite a lot more in terms of other weld repairs, other scenarios, etc., etc. And there's quite a lot more to show in terms of panel making on the Jaguar. So what I'm going to move on to now is, and getting my phone out so I can have a little look. There were some questions which I picked up on. I will have missed some. Don't worry, just ask more. Ask questions about previous videos if you want, whatever. But I picked up a few questions from the previous video, largely around the blasting. So I'm going to answer a few of them. The first one was grit recycling. Do we do grit recycling? Yes, we do to a point. The crushed glass, as pointed out by a few people, does break down. Yes, it does. It breaks down quite rapidly and it turns to more or less a talc. What we do is we kind of use that to an advantage. We used to buy a mixed grade of glass and use the fact that it was supplied with a variety of particle sizes to our advantage in order to get the surface finish. I'm trying to think of an analogy here. If you know anything about shotgun pellets, I guess, I don't exactly know what the pellet sizes are, but basically if you imagine shooting a panel with a shotgun with a single shot in it, you're going to make a really big hole and do some real damage in one spot. If you use very fine shot, you're going to do very broad spread of damage, but it won't be nearly as bad, the damage. Similar with the blasting grit. If you're trying to remove heavy corrosion, if you use large grades of grit, large screenings of grit, each time a piece of that grit hits, it'll do a good job of removing the corrosion. But it won't cover an area very quickly. If you use very fine, it'll cover an area very quickly and generally clean the whole area, but it might not remove the deeper parts of the corrosion. So what we used to do was buy a mixed grit in. We don't now. We buy what's called a medium. I can't remember the exact particle size. It's what the supplier terms as medium grit. We buy that in, which is actually at the coarser end of what we would want, but we remix it with screened previous grit. And I actually built a vibrating screen deck, which we'll just show a shot of in a minute. Built a vibrating screen deck, and when we finish blasting the car, we shovel all the grit up off the floor, we run it through the vibrating screen deck, and that screens out the very fine material, which we discard, that goes to landfill, and then we screen out the particles of stuff, bits of paint and things like that, and other debris and detritus and lumps that could block the blaster. They go to landfill, and then we screen out the middle fraction of good size, of the correct size grit, and we then remix that with new grit so that it gives us a spectrum of particle sizes, so that it then has a very good cleaning action. So that's what we do in terms of grit recycling. Yes, we do. Some goes to landfill. There was another side shoot to that question, which is what do we do with the lead? Noticing the lead falling off. Well, we actually gather up all the lead, and we've got a couple of big tubs of it. We have in the past, and we do every so often, remelt a load of used lead, purify it, and we've actually reused lead for lead filling. It's reusable a number of times. There are slight complications to that, but as long as you heat treat it correctly after you've remelted it, as long as you temper it properly, you can actually reuse the lead. So we have remelted, purified and cleaned and reused lead. So we certainly don't just do that. We've got that much now. I think at some point we're going to have a bit of a scrapping session because it's worth a reasonable amount as well. And we've probably got about 50 kilos of it kicking around. So at some point we probably need to weigh some in. But yeah, we gather up the lead, that gets stored. But yeah, all the other detritus, the paint and other sort of generic stuff that comes off, that's landfilled, so that's where that goes. I had another question here, which was somebody had talked about the detail on the process, and that, oh, it was on another site, so we wouldn't know. It is on this site. The blasting we do in-house. When we say we do it in-house, we literally mean it is done here. The blast room that you saw is here on our site. That's where it's done. So yes, it is all in-house, and yes, we deal with all the ins and outs to that process here. There was a question on soda blasting. I'm going to try and not get on my soapbox too much here, but my experience of soda blasting is at best disappointing. All the advantages of soda blasting that I can see are equally advantageous with glass grit blasting, and all the downsides of it are overcome with glass grit blasting, so I don't really see the benefit to it. the alleged benefits of soda blasting are that it's kind to surrounding things, and the classic example I've seen on a certain restoration equipment website is a picture of somebody soda blasting the side of a car on their drive with the glass and trim still installed in it. Well, that's an entirely pointless operation. What you're going to do after you've blasted it, it's now bare metal but with the trim still attached, which all needs to come off before you paint it. So that was a pointless exercise. And the other thing is that it's kind to panels. Well, it is. It's so kind to the panels that it won't remove the corrosion. If anybody's ever tried to soda blast corrosion away, you'll realise it won't touch it. Any soda blasters that are actually blasting corrosion away will be mixing crushed glass grit with the soda, which then negates the point. You might as well just use the crushed glass grit. I've heard there's a reference to using soda on engine parts, and that was a very appealing thing to me for a while, but a local company to me bought a very, very, very expensive, brand new, state-of-the-art soda blasting setup. They're an engine reconditioning company, quite a big one. And they bought that for cleaning cylinder heads. I warned them at the time I didn't think it would work, and it doesn't. It cleans them in about the same way as you can clean them with a powerful steam cleaner, but all the carbon deposits that are really hard are still there and it won't remove them. So to that end, it's a pretty pointless thing. So realistically, we would have zero use for soda blasting on this site. Having seen it done and having used the soda blasting setup for engine components, I would say it would be a complete waste of money. Don't even bother. And then the next question I had, which is a sort of spin-off from that one, is that I saw somebody mention dry ice blasting. Yes, a very interesting process. Totally useless on a body shell. Forget it. There was nothing that dry ice blasting would bring to that car body shell stripping that would be of any benefit at all. It's not aggressive enough to do any good on any of the things we saw last week on the previous episode on the body shell. However, it is actually a useful process. What I've discovered, having done it on some engine components, is it's actually very good at removing tar-type deposits from aluminium castings. It won't remove, it's very limited in its application in that even lightly corroded aluminium it won't clean up. So if you've got lightly corroded aluminium castings, you still generally need to bead blast them with glass bead, which is what we do with aluminium castings. Obviously the downside is on something like a cylinder head, doing that you fill the cylinder head with glass bead and you need to get every scrap of it back out again, which generally means taking it back to, I always think of it from the point of view of the production of the part. When the manufacturer produced that part, they bead blasted it, but they did it before they finished all the machining operations, which means that they could clean all the glass grit out. So what we do is we remove all the bungs, all the plugs, all of the things that give access to the casting, then we bead blast it, we can clean it through all those apertures that the manufacturer originally did, and then we put it all back together again. But it does mean taking every single plug and screw and widget out of that casting to be able to do that. Where the dry ice blasting benefits is it obviously doesn't put anything in the head. It disappears, it evaporates off to a gas, when it actually sublimes to a gas. And that's actually how it cleans. It actually cleans during the process of it sort of sublimating on impact. So the frozen particle of CO2 hits the surface and basically immediately turns to gas with the heat of the impact. And that seems to ablate I would call it ablating, that might be an exaggeration, but it basically smashes the tarry deposits off, because I think it kind of freezes them and chips them off at the same time. So it's very good at removing tarry deposits. No good whatsoever at cleaning a body shell though. Won't remove paint, won't remove corrosion, won't remove anything really that's on a car body shell at any appreciable rate. So that kind of covers those processes. And yeah, neither soda blasting nor dry ice blasting are of any great benefit on when cleaning a body shell up that has some corrosion on it and has some paint or paint residue on it. So that answers those. There are a few other really good points. I'd spotted a point, I haven't put it on my phone actually, but there was a guy who talked about offshore installations using blasting and letting the hot rolled steel weather prior to blasting. That's exactly hit the nail on the head there. It's a really good process. You let the corrosion lift off the mill scale, which is extremely difficult to blast, and then you blast the corrosion off, which blasts very easily. That's a really good process. Dead on that. That's absolutely spot on. And and he commented about the zinc spraying, which is entirely on the nail as well. So yeah, good. Keep your comments coming. Hope you enjoy it, and yeah, watch this space for the next episode. We'll do a bit more of a dive into how we make bits of metal to fit cars that have fallen apart.